Hi, welcome to page 2 of version 2B for fall 18 Chem 8A exams. We're going to be adding curved arrows to finish the mechanisms given. And we're going to make a nice little list of bonds broken and bonds formed. We'll go one at a time on the stuff that's changed. We can see that this oxygen here is the same as that one there, and that oxygen is in a single bond in the starting material, but in a double bond in the product. So we're going to make sure to note that we're going to be doing that. That's going to be part of our arrows. We'll then take a look at the next atom. We'll see that we have a carbon here. We've already taken care of the fact that we formed a carbon-oxygen pi bond. So let's look over here and see what else is different. Oh boy, we see that this chlorine is missing. There's only one chlorine, but I'll highlight it because it's fun. That chlorine is missing, so it's going to be a big thing to add that we have broken a carbon-chlorine bond. And I think that's it. So let's just go ahead and add those arrows. We're going to start at electron-rich, the most electron-rich region. This might be just a simple lone pair, or it might be a pi bond, or it could be a negative charge, which is kind of the same thing as having a lone pair. We're going to make sure that we're ending at a more electron-poor part, which is maybe harder to see from the beginning. I'll zoom in on this so we can see real well that we're going to start at the oxygen lone pair and kick those electrons down to the pi bond. Check. And then too many bonds around carbon, so we're going to kick these electrons starting at the bond and end at the chlorine, and that explains why this chlorine has a negative charge. So that does it for the first part. We'll do the same thing for part 2. We have focusing on this first step, so it's one thing at a time. We notice that the main difference is what's happening on this oxygen. It goes from having no hydrogens to having one. So we're going to make sure that we're forming an oxygen-hydrogen bond. We also see that that hydrogen had to come from somewhere, so we can make a little note of the other part, which is this HCl molecule that we start with, we can see is torn apart into two somehow. We're going to be breaking a hydrogen chlorine bond. Since we know that we go from an oxygen that is neutral to an oxygen that's positive, that means oxygen must have shared its electrons. So we can start at this oxygen, end at the hydrogen. Gonna start at this bond, and end at the chlorine. And that's how we make this protonated epoxide. In the second step, we'll look at other stuff that is different. We will look first at, let's say, this oxygen. We can see that this oxygen is bound to 2 carbons and a hydrogen, whereas over here, it's only bound to 1 carbon and a hydrogen. So that's going to be a big thing. We're going to be breaking, in this step, a carbon-oxygen bond. Other stuff that's different. We have, starting with this chlorine that's hanging out by itself, is now bound to a carbon. So that must mean that we're going to be forming a carbon-chlorine bond. Right? That wasn't there in the starting material. We are going to start at electron-rich, which in this case is the chlorine with a negative charge, and we're going to end at electron-poor, which at first glance, don't do this, but at first glance looks like we should go from negative to positive, but we don't see an oxygen-chlorine bond in the product, so we know that something else must be happening. The electrophile is instead the carbon, because again, we're looking to form a carbon-chlorine bond. We start at the chlorine, we end at the carbon, take these 2 electrons, kick them onto oxygen, and that's how we carry out that epoxide opening reaction. You'll learn more about this reaction in chapter 18 in Chem 8B, but it's pretty similar to the epoxide opening reaction you learned in chapter 8. And by the way, the one up above here, you'll learn in chapter 21. That's Chem 8B material as well. Now for part B, I already made the video for that. The one on version A is exactly the same as version B. It took me a little while to make that, so instead of doing it again, I'm just going to direct you to that separate video for version A. We then move on to these carbocation rearrangements. We want to take a look at the stuff that's changed, so these 2 areas. And specifically, I'm going to go through, since the carbon skeleton hasn't changed, I'm going to make little notes of where I have hydrogens. This only has one hydrogen because it's given a positive charge. So it's implied that there's only one hydrogen there. If we look at our product, we see there's no hydrogens there, ooh, and we have two hydrogens here. That must mean that the tertiary hydrogen must have moved over to the secondary carbocation. Very important to start that arrow at the bond and end at the carbon of the carbocation. This is referred to as a hydride shift. A hydride is a hydrogen with its two electrons. That ion doesn't really exist to a big extent. It's typically liberated in another way, and it's liberated just like this, where the hydrogen leaves and it takes its electrons with it. That's the first carbocation rearrangement via hydride shift. The next one seems a little more tricky. Big deal, you're going from a 4-membered ring to a 5-membered ring. So that means we're breaking the carbon skeleton. This is going to be known as an alkyl shift. We're going to have to break one of the carbon-carbon bonds in the ring, and we're going to have to form a different carbon-carbon bond. These alkyl shifts tend to happen when you have carbocations with a quaternary carbon. This guy is a quaternary carbon next door. We're going to have to open up that ring to make this happen. And we'll try and make it clear by numbering our carbons in the starting material and see if we can identify the carbons in the product. And we're just going to start here. This is going to be carbon number 1, which is connected to 2, 3, 4, 5, and then by default, this must be connected to 6. So we're going to get a little more specific on which bonds are broken and formed. We can see in the starting material that there is a bond between 2 and 5, but no 2 to 5 bond in the product. So that's a big deal that the carbon 2 to 5 bond is going to be broken. And in the starting material, what else is different? We have 5 and 6 being separate, and then in the product, we see that they are now together. So 5 to 6 is going to be formed. Right. We're going to start at the bond being broken, and that bond is the 2 to 5 bond. We're going to end at carbon 6. So we're donating electrons to carbon 6. This is now part of a carbon-carbon, or that's now part of the ring, where it has carbon 2 on one side and 5 on the other. And the carbocation indirectly then moved onto carbon 2 because carbon 2 lost electrons and didn't get any back. And that's the alkyl shift problem. Finally, part D is very similar, or is exactly the same in version A. Curved arrows were not necessary. It's just making a carbocation, identifying that this is a Markovnikov addition, that this is going to go to the more substituted carbon of the alkene eventually, and that this is going to go to the less substituted. If you remember, in the first step, you're going to be adding the hydrogen. In the second step, you add the bromine. So that means this intermediate only has the newly added hydrogen and the carbocation on the more highly substituted carbon. Not necessary to put the hydrogen here, but you can if you want. It's just showing the new thing. And that's it. That's the carbocation stuff. And then the only other thing that's different for version B is the very last multi-step synthesis problem. So you can find all the other version B solutions that are the same. In version A, it's just a little bit, the single step reactions are reorders. So happy listening and watching.